ADMEC, that is a small company that believes that research is necessary to grow up in this economy, and in particular it wants that its work was sharing with scientific community in order to make new ideas and to develop new devices that can help the community, like health. In particular, we work with the Polytechnic of Torino, the youth, and the University. And we are interested in pulse wave because pulse waves are generated by cardiac cycle and then transmitted along the arterial tree. So it amplifies the signal, and it's different from point to point in this arterial tree. That means that we can recognize cardiovascular disease from the modification of pulse wave. We are interested in pulse waves, in particular with vibration transmission in the artery and its surrounding tissue. In particular, we are studying the radial artery in the wrist that is located here. This is the radial artery in the left hand, and this is our Tafel and other authors also describe the artery. This is the tunica media. This is the adventitio, and we consider also the tissue around here, the dermis, the reticular dermis. We neglected the tunica intima and the fat layer because they are so thin in this region that we can neglect it. We consider also this material, this sandwich, this complex system made by two components. The first one is the ground matrix, and the other one is the fiber. In particular, we take the matrix as an isotropic material, so the anisotropy comes from the fiber. We choose to model the fiber distribution, the fiber orientation with a statistical distribution in order to get better results in the mechanical of this tissue. In particular, this kind of integral, when you use a numerical method like finite element implementation, you need to calculate this numerically and use a particular method called spectral design. In our problem, we assume a couple of things. One is that our system is an incompressible hyperelastic solid made by fiber in ground matrix. We also have a constraint about the separation, so the volumetric fraction of fiber and the volumetric fraction of matrix has to be 1. We also assume that these phases have the same velocity. Also, we suppose that the media of the system have a transversally isotropic behavior. We'll look the deformation under a particular variational formulation, the 3-variational field of Uashitsu, and an augmented Lagrangian. And for the remodeling, we consider a remodeling variable of this intelligence. The problem is set mechanically in the first part with classical equation, I can say. In particular, we constrain the incompressibility here, so we have intercept pressure there. The negatory part is taken from constitutionally, And instead for the remodeling, we said that the evolution of orientation of the fiber is described by the variation of the angle, of the mean angle that we take. And this is given by a balance between the internal and the external remodeling forces, with other absorption that we mentioned above, so incompressibility, same velocities, and transversally isotropic. We split the third function between the layers. So this is the characteristic function that identifies the layer. This is the particular energy function of the layer. So we look the volume fraction of matrix, its energy function, the volume fraction of fiber, and then the energy function for the fiber. We split the matrix energy in two parts, a volumetric one and a distortional one. For the fibers, we consider an isotropic contribution and an isotropic one. That's how we mentioned above. This is made with a probability density distribution. In particular, we take an EUCAN for the distortional part of matrix and the isotropic part of the fiber. And here, for the isotropy that appear in the fiber anisotropy, we have an activation function, an Heaviside function that is not null just when we have an elongation, not a compression, and an exponential function. All these functions are polyconvex, how we can see in the works of Neff. The importance of polyconvexity is that we need the existence of a solution when we treat a structural problem. Like this one, this is a boundary problem. It not guarantee the uniqueness. So probably we can have some numerical instability, but the solution exists. At least one. At least one. Here, probably, there are two invariants. The first one is the trace of the choric part of the right cosheaf tensor, and this one is always the choric part. And here we have a structure tensor that depends on M. M is the unit vector that characterizes the direction of the fiber. And this invariant is also equal to the square of elongation. For the deviatoric part of the first Kirchhoff tensor, we split the contribution of layers. So we have three contributions: the media, the adventitia, and the dermis. Each contribution is viewed as the deviatoric part, like the derivative of the energy function. So we can use the split of the three components: the matrix, the fiber, the isotropic fiber, and the anisotropic part. In this way, we study a three-field variational form. The three fields are displacement, volumetric parameter, you can say, and hydrostatic pressure. So we have the classical power variation of 4. Here we constrain the determinant of the gradient of the deformation to be equal to volumetric parameter, and then here we constrain the pressure to be equal to the derivative of the volumetric part, but we had this part that let us to use an augmented Lagrange method. In particular, this is the parameter corresponding. And if you use a finite element that I have a low order polynomial interpolation, then you can get some numerical problem like locking phenomena. In this case, there are two techniques possible. One is to choose two different degrees for displacement and for pressure and volumetric part, and then in particular inside each element choose a median addition. That means a constant interpolation between elements, where we have the current volume over the reference one, and for the pressure we derive this function, and then we use this value that we set. In our simulation, in the previous start point, we use just one-dimensional. With our study to overcome this problem, but for now we have just this one. We assume just radial displacement. We neglect the body force. We suppose that at an end point we have just a compression. In the other side we have an tension. In this case we have no remodeling in our simulation. It's just a starting point. We are working on this problem. And so this the problem that we are trying to solve. For the geometry, we take standard histological information. So the radial artery has 2.5 millimeter at wrist. The media is quite thick if you compare with adventitia, and then the reticular dermis that compose the grid part of this system. Using a finite element implementation in matter, we discover this decreasing of displacement along the thickness of the system. And in particular, we get this result, 10 micrometers, that are quite comparable with some other works, or something in particular, for a tension that is systolic pressure, 120 millimeter of mercury. Here, so at the dermis surface, we can see how low is displacement. So how we work about displacement and internal pressure in an artery is quite hard, because you can see the movement of the skin above. But we want to measure in some way this parameter in order to recover then the pulse wave and recognize from this a cardiovascular disease. So if you want, this is some reference that you can see for more details. So it's okay. Thank you.
Just
Thank you.
Maybe you know the model by Remodeling for a rubber with magnetic particles embedded. That it's incompressible, and also there is a direct run, and this is a transfer, so it's a drop meter. So maybe it could be of help for your modeling of the tissue itself. I don't know.
Okay, yeah, sure. Probably we want to take a more detailed model to take advantage between the fluid in the system. Also, the fat layer could be an important fact because not everyone is equal to another one. So, if you want to study another point, not here but the carotid artery, you need to consider the other parameters. So, thanks for the suggestion.
I also joined to thank you for the nice presentation. I have only short comment. In general, such biological arteries have some kind of helical symmetry, and also they have pre-stresses. Because when you cut them, you obtain some deformations. And this pre-stresses is very important for modeling of behavior, because it's not simply nonlinear elastic, transversal or something, but with some non-homogeneous and with the initial stresses.
We are addressing this phenomenon for now, but we hope to take also this important phenomenon in our model. We try also to study a general way to study arteries and the surrounding tissue to not specify the artery, because for example, carotid is very elastic. Radial artery is a muscular artery that is quite different in mechanics. So we try to get this difference by step by step. Step by step. Yes.
Yeah, I mean, you have built a nice model whereby you combine Faber matrix composite and integrating some hyperelastic model for each of the constituents. One of the difficulties in the hyperelastic model are the identification of the parameters for each of these models. In the case that you present here, which is basically the radial expansion, assuming that you have two orientations of the fibers, is kind of biaxial sort of tension on the wall surface. Okay, and my question is therefore, have you any idea how you plan to identify for any kind of loads the parameters of each of the hyperelastic model, and how you think of implementing that?
For the moment, we get the data by histological information that are covered from a scientific group of University of Padua that are the mechanical department that are working on it. It's a huge problem because in an economic view, you need to identify the parameter of each person. For the moment, with the experiment about tissue, we delegate this work to other departments, but we have to consider also this, because identification parameter is a huge work, and also modeling is very huge. So for now, we are focused on modeling. Then, step by step, with time and some economical entry, then we can look at the other models. Thank you.
Okay, thank you very much.